All right, day 15, rambunctious recitation. This is another one that I didn't do live coding. I've been trying to live code, but sometimes these problems require a little more just time for me to think about them and how I'm going to approach them. So I'm just going to give you a run through of my solution for parts 1 and 2. So essentially what's going on here is you're playing a memory game with the elves, and the players take turns saying numbers. They begin by taking turns reading from a list of initial inputs, so these seed numbers, these starting numbers, and then each turn consists of considering the most recently spoken number. Now, if this is the first time the number was spoken, the current player says 0. Otherwise, the number had been spoken before, and you want to find out how many turns apart the number was from when it was previously spoken. So we need to keep track of two things. What was the last number, or three things, I guess. What was the last number spoken? If the last number, was it the first time that number was spoken? And how long ago was that number spoken if it wasn't the first time? Three things we need to keep track of. So in this case, they give us a run through of this example. So of the case 036 for the starting numbers, on turn 1, first number is a starting number, so we skip it. Second, starting number, skip it. Third is, and then on turn 4, then we have to consider 6. Now, this is the last number spoken. Since it was the first time the number had been spoken, the fourth number spoken is 0. On turn 5, the last number spoken is 0. It had been spoken before because that was a starting number. And now we just need to find the difference between the turn number of when it was last spoken, which was the previous turn 4, and the turn number of the time it was spoken before then, turn number 1. And the fifth number spoken because of that is 3. 4 minus 1 is 3. The last number spoken, 3, had also been spoken before, most recently on turns 5 and 2. So the sixth number spoken is 5 minus 2, 3. On turn 7, since 3 was just spoken twice in a row, and the last two turns are one turn apart, the seventh number spoken is 1. On turn 8, 1 is new, so the eighth number spoken is 0 because of this first rule here. On turn 9, it was last spoken on 8 and 4, so the ninth number spoken is the difference between them, 4. On turn 10, 4 is a new number, so it's 0. I'm sure there's a trick here with the numbers and when they're being repeated, or if they're being repeated, and like how frequently you can expect zeros. I just did a brute force solution to this. I went through and just computed based on the previous numbers. Initially, my solution, I used a list, and I just kept track of everything spoken, and that I would just look up the last time a number was spoken and then subtract that index. And that was fine for the first example, which is 2020. That finished in a reasonable amount of time, but the part 2 gives you this 30 millionth number, which is much more complex. And if your solution is not optimized, it's going to peg your CPU and you're going to be using a lot of memory. So I ended up rewriting my first solution so that it would be optimal for the second one. And what I did was I kept track of, I have this set of this lookbacks map, and I'm using this thing that's a Google Guava construct called an evicting queue. And this is a queue it's a FIFO queue, so the first in, first out, and then you give it a size, and it will automatically evict anything that's like if the size is 2 and you have 2 numbers in there and you try to add another one, it'll evict the least recently added number and put the new one onto the queue. So that's really all we need to keep track of, is like when was the last time. Like this eviction queue tells us two things. It tells us how many, like has this number been spoken once or more than once, and when was the last index of, like when were the 2 last indexes when it was spoken. So I initialize that by clearing the mutable map, and then I go through the inputs initially and I add them to this lookbacks table. And I'm using this compute method, which is it's a method that Kotlin has on maps where you can compute a value for, you can compute this, this is kind of misleading because this really is the key, but I'm wanting it to use this value as the key. So I'm computing this key, and then if the queue is not initialized, I'm initializing it, and then I'm adding this index to it. So this is the index of when this number value was seen, and then I'm returning the queue to this value. So it's going to have a map of these values, like 0, 3, and 6, to a queue of the last two indexes at which they were seen. So after we initialize that, we loop through, and we take, this takes in a stop value, and that's when to stop. We initialize the lookbacks, clear the map, set the inputs to it, and then we start at this input.size, and you step through it. So to speak, if the lookbacks at last spoken, which is the last one in the input, if that input has only been spoken once, then we return 0, which is this first rule here. Current player says 0. Otherwise, it is not the first time. It has been spoken more than once. And so we take the first item in the queue, because remember it's a FIFO queue. So the first one is going to be the first occurrence that we know of. Like, we have a very short-term memory here. We only care about the most recent time that it was spoken. I'm adding 1 here because I'm using this index. Really the right way to do this would be last spoken, the first one minus the last one. This would be last, minus the first. There we go. So we're taking and this last is always going to be the previous index. So we could actually do I minus 1, because it's always going to be the previous index that we've seen this. So I minus 1 minus the lookbacks last spoken, the first value, and then we're setting this to speak. We have this pointer basically to this is basically like the current value, and we have to update that with what we just spoke, and then we're updating the lookbacks with the last spoken value. We're looping through, doing that until we get to this stop value, and then we're done, and then we return this last spoken value. So pretty straightforward. Like I said, my initial approach was just to keep track of all of this in a list, and that ended up just being way too heavy on memory and just unnecessary, because you really don't need to keep track of everything you've spoken. You only need to keep track of those 3 things I talked about, and you can have a much lighter weight memory footprint with this approach. It does solve pretty quickly. Let me see here. I have day 15 test. I did just change that, so I hope I didn't introduce a bug that this is not going to pass now, but and I wrote some tests around the example input that they gave us, and then the values and everything. I wonder if I messed up here. There we go. I think it's just, I'm using a lot of resources recording this. It was definitely going faster earlier. There we go. So it's able to solve this part 2 in 500 milliseconds, which is reasonable. It was taking like 20 minutes before, and at that point, you just have to, if it takes longer than a minute or 2, you probably are not having an optimal solution. Part 2 full input was 14 seconds, so it's a little, I see, this was a 14 seconds, 500 milliseconds. So yeah, part 2, I think no matter what, it's gonna take a bit longer, because the number that you're solving for is so much more complex than this one. So anyway, hope it was helpful. I found this one overall pretty straightforward. If you have any questions, feel free to comment in the YouTube comments, and then I am including a link to my repo in the description for the video. So, as always, thanks for watching.